the end-to-end demonstrations through key applications will be on predicting flat ocean continuum and what-if scenario for nature-based solutions. And one end-to-end predicting system is challenging because we have to consider the interaction between the very different model components, which is very important. But from the other side, such a predicting system is not of interest if it's not linked first to the large-scale models through downscaling or zooming, but second, it's not linked with the atmosphere, waves, hydrology, or land use models. But in order to consider these two challenges, of course, we have to deal with lots of diversity of the model components, which are very different. Waves model, a spectral model, we have Navier-Stokes model, or we have the biogeochemical model, but also with the different time and space scales. But such system is not if the synergy between the coastal system and the newly available data, we have heard a lot about that yesterday, about the new sensors for coastal application, is not ensured. The system has to solve the practical problems. It has to work for both operational design, demonstration, but also for climate change. And this system has to respond to the end users and social demands. And in the institute, we developed the GESCAH coastal model system, GCOS, which is not a model. This is a modular system, which means that some model can be taken out or added. And then it consists of the different elements, namely the atmosphere, waves, ocean interaction, the dynamics and fluxes of the land-sea transition and the coupling of the marine hydrosphere and the biosphere. And we did it with the different what-if scenario for the nature-based solutions, namely in the aggregating observations and coupled model, which is very important that we use both the synergy between the hydromorpho ecosystem models and the observations, and then going for making and develop the tools for assessing the risk across the different scales. And then we have in such system also to consider the uncertainties for the multi-risk projections, because all these projections, they are connected with high level of uncertainties. And this end-to-end system can be then used for the nature-based solutions and the what-if demonstrator. And for example, for that is considering the seagrass for scaling up risk reduction as a function of the active and passive restoration. And scaling up means that if the system is developed and tested in one region, then we can upscale it to many different regions, and I will provide you here some example of that. And as an end result of this system, we can make an assessment which can be done co-developed together with the stakeholders and policymakers. And this risk assessment can be done with and without nature-based solutions, and then study the limits. And such a system has a different layer of workflow and integration. And I give you just one example here, which is the schism framework. This is a framework, not a model, because in addition to the standard parameters and models, which are hydrodynamics and waves, it includes biogeochemical, which can be either integrated or externally coupled, sediment dynamics, water quality model, oil spill model, drifters. And we do the workflow at the different levels. First, we start with the forecast level, in which we forecast, for example, water level, morphodynamics, hydrodynamics, and nutrients. Then we continue with the data level, in which the different nature-based solutions can be analyzed. For example, engineering reconstructions versus green solutions. Then the next level, which is important for intermediate users, but also for the scientists, is the analysis mode, which is the risk assessment. This risk assessment can be done in two-way integration between scientists and end users. And then it depends whether this is on the flooding, on the erosion, or for the ecosystem services, which includes the carbon sink and water quality. And finally, it ends up with the products. And these products can be either risk maps or warning alerts or projections and scenario. And since I'm not here in the afternoon and we discuss the motivation of adding the Wadden-Sea region as one of the key area, is because this is a very highly energetic system. From the other side, it has a very rich ecosystem with very rich variety, but this is also an important infrastructure. And regarding the nature-based solution in the seagrass, the recent observations said that there are trends of recovery in the northern part of the area, but still there is a very sparse population in the southern coast. And this is why with this kind of what-if scenarios, we are able to evaluate the ecosystem services which are provided by the seagrass with respect of the hydrodynamics and wave dynamics. And in general, the Wadden Sea is a living lab in which the different scenarios can be tested in the nature. And I will provide you here different examples very briefly without going into details, because all details can be found in publications and they will come later. The first one is the what if in biodiversity, in which the system considers the biogeochemical model ECOSMO. And this is a realistic model, which actually considers not only a structure grid. This is a relocatable model for the land-ocean continuum with full tidal wetting and drying, the freshwater continuum. And this has been also implemented not only for the Wadden Sea region, but for the Baltic Sea region as well as for the estuaries and harbors. And we demonstrated that this predicting modeling tool delivers a realistic picture of the estuarine processes, and then it can be used for the what-if scenario for changing the nutrients and the water quality, but as well as for the what-if scenarios for the oxygen depletion. And the pattern here shows the oxygen limitation along the Elbe River. So you see here, this is a section along the Elbe River, but it can be also considered for the what-if scenario for changing the hypoxia, for example, with the climate change, the sea level rise. And we can produce the risk maps for the water quality parameters. And as an example here, I show the organic sediment and near bottom dissolved organic concentration for a very high resolution Hamburg Harbor. You see here is a Hamburg Harbor, and you can see that especially the near bottom dissolved oxygen concentration is extremely high there. Then the second example, this is the what if for nature-based solution that I have already mentioned. And just to give you an illustration, on the left-hand side, you see the standard management protections, which are the engineering solutions for the coastal erosion, which of course for tourists and the population don't look nice. And from the right-hand side, those are the green solution, which provides an innovative alternative solutions, which are nature-based solutions that can be used for the coastal erosion. And in respect of the Wadden Sea, there are two different types of the seagrass. And as an example here, we evaluated the seagrass as a nature-based solution for coastal protection. And here, this is just one example for the German Wadden Sea area, in which we applied the Capot model, which includes hydrodynamics, wave dynamics, and sediment dynamics. They all interact each other, so they have full two-way interactions with and without vegetation, in order to identify the reduction of the coastal energy, which is due to the extent of the seagrass coverage of the different areas, not only within the German Bight, but we also transfer it to the other areas. And from observations, we can assess, we have areas with more concentration of seagrass or with less concentration with seagrass. But the sweet things of having modeling too is that we can play and make a limited number of runs and scenarios. And we really played a lot. For example, we did extreme scenarios with either no seagrass, which happens in many areas around Europe or in the world as well, but also scenarios with absolute coverage with seagrass. Of course, we know it's not realistic, but we just really wanted to see and to optimize. And of course, if you want to optimize, then you go with make it further realistic scenarios. And then with that, we also assessed the waves and the impact on the vegetation together with the sediment concentration, which also interact each other on both the waves and the currents. And then we show that the overall stress, of course, with vegetation is reduced. We analyze not only mean conditions, but also the extremes. And then the results really indicated a strongly reduced of erosion, which is reflected within the reduction of the simulated bottom layer sediment concentration. And then we show that up to 50% and also 100% in the extreme restoration scenarios came to the coastal, reduction of the coastal erosion. And as a conclusion here with these different what-if scenarios, that the seagrass changes the hydromorphodynamics conditions by reducing erosions and facilitating increase of the sediment dynamics. As I mentioned, in these experiments, sediments also played an active role. But also the seagrass expansion helped the tidal floodplain growing to keep up with the sea level rise, because a branch of the experiments have been also reflected with the sea level rise, which can be taken into consideration within the modeling system. And this also reduced the flood risk. And then also the seagrass expansion can be useful addition to engineering coastal protections. We had many meetings with the stakeholders, with the intermediate and end users. And here just a message is that we have to be very careful when we communicate it and work with them, and also define scenarios, because they are always very careful. Yeah, nature-based solutions, seagrass, it cannot be a solution for coastal protections in Germany or neither in the Netherlands. So be very careful. You're scientists, you do whatever you want. But then if you come to us and say, forget about engineering construction, do it only nature-based solution, we are not going to pay attention. But then all these communications and interaction should come in a way that there should be intermediate solutions. In some places, of course, coastal protections through the engineering constructions are very important, but also in combination with the nature-based solutions, we can have a really very nice solution in the future. And then to extend it further, this exercise, we made it what if nature-based storm buffers on mitigated coastal erosion. So in addition to all this system that I already explained it, then we added also the morphodynamical model X beach, and then we studied with and without seagrass, also the changes of the bathymetry and the coastal erosion, the changes of the coastal lines. Of course, here another problem is that it's for the discussion is that the bathymetry, which is an input, is not available. So we had first to develop this in the area where we got sufficient bathymetric data. But nevertheless, this can be also done for what-if scenarios to identify the most effective seagrass placement. So this was a completely different branch of experiments in which we did more than 200 different scenarios. And really we played not only with the grass head, but also placing it in the very different roles. And then we show that the bathymetry changes, the roller and the wave changes, especially near the coastal areas. But also what has been demonstrated is that the size of the meadow and the sensitivity of the different study actually is not to what you expect. You have many meadows on the real near coastal area, and then you have the reduction of the coastal erosion, but another way out. If you go it further, oh, it doesn't work. It's no, but nothing changed now. Oops. Now, now it was very quick. Yeah. Anyway, so you see now all my presentation, but I'm then close to the end. F5, I don't know which. Yeah. And then we showed then that the most significant decrease of the erosion is not achieved by the starting seagrass planning, but also in the terms of the intermediate water depths. And this was the scenario. So what I show is that with the use of the real-time observing system and the model frameworks, which are already mature enough to be applied for certain areas, then we can make it step further and integrate it into the digital twin framework. This is what we are planning to do within the Editor Model Lab project, which is European project that started this year, and there are many also here in the room that are attending the project and that will contribute. And then where the digital twin starts is for the integrating this infrastructure that has been developed by scientists into a platform that can be used for not only the what if scenario, but also for the different applications. And then I will then very briefly show you how these scenarios and what if scenarios then further can be transferred to the digital twin. And you remember yesterday we discussed a lot about the relocatable system and how we do this relocation. And since we develop what if scenarios for the nature-based solutions for certain areas, by this relocation, they can be extended and this can be used in addition to the seagrass, also to study the effects on the mangroves. I will show one example here for the coast of Ghana, but also to study the coastal erosion with the dunes, which is a very important, but as well as the impact for the oyster, which also changes the bottom friction, and then for the salt marshes. And then all these nature-based solutions, they have to be co-designed with the stakeholders, which is very important. Once we develop the digital twin, then the what if scenarios, they will be co-designed with the stakeholders, and then they will include the human impacted what if scenarios, which will be designed to improve the protection of the local community and the ecosystem, and also the mitigation of the impact of the floods, but also the storms or droughts. And then they will be combined with the climate change. And here, this is an example of how the digital twin framework for what if scenario for the nature-based solution can look like. First, we have the problem and the solutions that needs to be tested. For example, the problem can be the European coast, flooding and coastal erosion. And then the solution is the coastal seagrass potential nature-based solution. Then the digital twin framework, which will be designed, which will include the different model components together with the observing system. And then the different what if scenarios can be developed. For example, what is the wave reduction due to the seagrass sediment, and the other way out, what is the effect of the seagrass on climate change, on the extreme events and the impact. I almost end here. I just promised to give an example for the allocating and transferring from grass to the mangrove trees. And then we started with Mankoga project to develop the digital twin solutions together with scientists of the University of Ghana, who will come and then work in our departments for several months, several years, in which we will want to develop the end-to-end platform, which will provide new products that can be available for the intermediate and end user in Ghana, and then they can be used for predicting playing the role of the mangroves as nature-based solutions for flooding and erosions at the coast of Ghana. And I think that here I stop because
Thank you.
it sticks anyway.
Thank
I say thank you.
Yeah.
Somehow in the morning, the PowerPoint doesn't work.
Thank you. It was an inspiring presentation. Any question from the public? Yeah, two.
Thank you, Joanna. That was a really great overview of what you're working on. You mentioned in the Wadden that you went to some end users, or was it policymakers? Who did you approach them yourselves, or was there an intermediate?
We have intermediate users, which actually they are decision makers, but also modelers. For example, the federal agencies with whom we are working, because federal agencies, they have also the role in Germany, the role for giving permissions to the decision makers, also with the trilateral Wadensi forum, but also with many real end users from the city, especially the coastal cities, and many others. So we did also end users a workshop, and we have also lots of bilateral meetings, which are very important, face to face, not online now. Really, to have it, especially with the decision makers, because otherwise, I told you, there's so many scientists, and all projects now, they have to touch the end users. At some point, end users, they are fed up of scientists. So we really have to make the different chain of interaction in order to convince them that if we do something together, and if they are involved in this implementation from the very beginning, then something can move forward.
Yeah, thank you.
So, I mean, I know it is difficult now to discuss this, but I think that we need also in cost predict for the digital twins that we could envisage to really point out the observational requirements for validating these models, because we really sometimes believe without seeing. And what is the most important? I know bathymetry, you said bathymetry requirement for digital twins. We need a very high resolution bathymetry.
And coastline.
Coastline.
Coastline is very important.
But what is the next to come?
Of course, I gave a very brief example for the what if for biodiversity. And when we are talking of biogeochemical parameters, and there is a really a big problem, what is available. For example, we are doing that for the Elbe estuary, for the German Bight, but also transfer it for the Baltic Sea, also for the Black Sea. And there's absolute lots of observation when it comes to biogeochemical parameters. When it comes to biogeochemical parameters, first, only very few are measured compared with the very complex models that we are using or you're using. DFM model have 39 variables, our model have 27 variables, but how many we can really assess? Very few of them. And even if they are assessed, even if we collect the data, they are with the different units, they are completely different, so they are hardly of use. Basically, from the Argo, we use oxygen data, which is very nice. There are very few chlorophyll data, but not so much. In terms of nature-based solution for the Wadden Sea area, they're very good observation of record for the seagrass, which is available, which is very good. But we don't have this information because we are applying the same system we are about also for the Danube Delta, and then it is lacking. Of course, with the satellite data, high resolution satellite data, one can retrieve the nowadays information, but it is impossible to go in the history. What is very important is the low-cost sensors, which are now intensively used also in our institute, for example, over the Elbe estuary and river. We have also these drones applications, which are very cheap. And then all those cheap low-cost sensors, they can be a really very good alternative. And of course, the new satellite data that are about to come, we all know about them. They are with high resolution.
Yep. Thank you. So we now move to the next presentation by Joao Souza from the Meteorological Service of New Zealand, presenting the end-to-end forecast system using a ship-based motion observation.
Oh my God. Oh man. All right, you let me know. Thank you. Thank you very much. It's a pleasure to be here. And actually, Joan's presentation was a nice introduction for some things that I have to say today. So my name is João Souza. I work for the Meteorological Service of New Zealand. And I would like to start by acknowledging my two co-authors, Colette and Julie. They actually did a lot of the heavy lifting here, but also all the other people participating in the MONA project. That's what I'm going to talk about today. So the MONA project is a pretty big project for New Zealand standards. And we started with 16 different institutions, both in New Zealand and abroad. And actually now, now that we're getting to the end of the project, we have 38 different institutions participate, because we kept engaging with all the main stakeholders in New Zealand, so all many fishing industries, government agencies, and we kind of brought them all into the project. We're assimilating them into the project. Everybody wants to participate, so it's pretty cool. It gives some confidence that we're doing something that's important. So it's a big project. There's a lot of things involved, but I just want to talk about two of the main components. So that's about observations and getting to models and providing forecasts. So everything started with a bunch of smart people in New Zealand before my time there, got together, and they wanted to be able to observe the ocean and forecast the ocean, and said, "Damn, we don't have observations." But then if you look where we don't have observations, it's actually all the coastal area, all the shallow areas, like below 1,000 meters, basically where Argo doesn't get. And that's exactly where all the fishing is happening. So they came up with this idea: what happened if we actually use all these different fishing vessels as observation platforms? So that's exactly what we did. We developed a new sensor, and this one that I have in my hand over here, we call it Mangopari. And Mangopari is a hammerhead shark in Te Reo Maori. So that's because we have a lot of iwi partners. And the idea is that to be a fully automated system and really cost effective and cheap. And by fully automated, what I mean is that something that the fishermen don't need to interact with, because you can't give another job to the fishermen, or they don't want to do that. They want to fish. So it gets in the water, starts measuring, change strategy in terms of how frequently it measures, feels the pressure and can change a little bit. And when it pops out of the water, transmits the data directly to a deck box that's solar powered. So no need to interact with the fishing vessel systems, and then transmits the data directly to us in real time. And so we can assimilate that into the models and provide a forecast right back to the fishermen at the boat. So it's an end-to-end, fully automated system. And as you see, it can be mounted at different kind of fishing gears, and that's the whole idea. So we can actually leverage all this different kind of fishing that happen. So that's more or less the map that we have. So that's the number of events per month. And so to the left, what you see is how many Argo we have around New Zealand. And not that many. So if we talk about the forecast system, that's by far not enough to constrain the ocean here, but actually a lot of people are interested. But then you look to the right, and that's how many Mangopari deployments we have per month now. And as you see, it's a lot more than Argo, and also covering the area where Argo doesn't get into. So great. And now we're going abroad. So we start with New Zealand, but right now we have a lot of different sensors in Australia, North Sea, US, South America, someplace in the Middle Eastern. We have a few in Greenland, under the ice in Greenland, and we started a pilot program in Antarctica. Cool. And just to give an idea of how many observations we talk about, and then in orange is the number of observations that we get from Mangopari in this domain around New Zealand, and in blue, how many observations we get from Argo. And we say, you see all the start where it started rolling out this, the sensors, so the first prototypes, and when we achieved the full rollout, that was September last year. So right now, these little guys are by far the biggest source of information of the ocean here around New Zealand. We have two versions, one that goes down to 200 meters, another one that goes down to 1,000 meters. We're working another one that can go deeper than that. Cool. So next stage, let's talk about models then. So we are operational agency. Our core business is to provide forecasts, right? So we have these different models around New Zealand. We have a national domain. That's what I showed the big map. We have to reformulate that completely when this project started. So now we had a long integration hindcast, so used to different process studies and to try to understand and correlate temperature to catch, so we can actually provide service to the fishermen. And we have some regional domains, and just put two examples of two different strategies. The top one is a structured grid, so a Rome's nest at the Bay of Plenty, that's the region. The reason that I present this one is because that's where the biggest mussel farm in the country is, and happens also to be owned by iwi, so a traditional population that's called Fakatohia. That's our main partner in this project. And I show another approach, that's a schism domain around Kaikoura, where most of the power or balloon fishing comes from. So then we actually of applying a wave circulation nest of a couple model there, so we can go actually to that near shore and try to understand what's happening. And then, so we have hindcast, we have a reanalysis at 25 plus years, so it's 28, and then we link into all nowcast to have a continuous coverage, and we have forecasts. And we have been using 40VAR, more specifically the RBL 40VAR, as a data simulation. And then we link all that to several different kinds of products so that people can use, so how people are gonna access the data, and I'm gonna talk a little bit more in detail about that. So the first question that we had is, okay, does it work? How good is it, right? So we run, just gonna show a couple of examples here. OSSE's ocean system simulation experiments for a period of time. So just got a period of time that actually had a setup of unprecedented marine heat waves around the country to try to understand how those sensors can help us to forecast some marine heat waves. So just to be quick here, so the black line is the unperturbed, so that's our reference. And then we had just a bunch of different OSSC's experiments. And what we see in general is that, yes, it works, but even if you simulate only the surface data, already improves things a lot. But when we started simulating the subsurface data, then actually we get thermocline depth way better, and we get a lot better results in the inshore. That's actually where we need. It's where people are interacting with the ocean. It's where the industry is. So this works, right? We're getting way better results, and we started getting a lot of attention from fishing fleet, and now we have a lot of attention from defense, New Zealand, because they want to know where the submarines are. So cool. But then, great, we have a system that works. We're simulating these observations, they're great, but now we have to provide this data back to the public in a usable way. So we have all these models, and then I just divided two kind of ways of deploying. We have data sets, so the model results and the observations themselves. Nessie is the supercomputer system that we use to run, so people can just go there and they provide them direct access to a few and select scientists that I trust. But also we have a thread server for everybody else to go. We have what we call the MOV, that's a web portal, that's Meta Ocean View. So that's a little bit more complicated. We have to log in and then have lots of options, and we provide direct API access. So if you want to run your own submodel, nested model out of our models, I can provide you an API key, so we can fully automate that. You don't need to go into the system and try to get access to stuff. And we also develop our own web page that's called Swell Map. So for people that are not scientists, they can interact with this data. So we have the maps for different depths, and you can navigate around, you can click and get what's the forecast going to be. We have a specific forecast for surfers, we have for fishermen, we have for boaters that give the information that they need. And we also develop tools. So develop Lagrangian tools, one that's specifically for pollution, plastic pollution, and another one that's a little bit more versatile. So we can look to anything floating in the water, substance, oil, and it's already directly linked to the data set. So again, the idea here is to be easy for the general user. So they need to understand a lot, download the data sets, link them, and doing anything like that. Just say, okay, I want to know where a container is going, and kind of have this setups already behind that make it easy. We have marine heat waves forecast. I'm going to show in a little bit. And now we're looking into machine learning and AI. So using this reanalysis, the training data set, and providing then a longer forecast, extending the forecast horizon. So again, talking about ocean forecast, that's my little view of how things work. We have different forecast horizons. Everything is red, the things that we're doing right now during the Mona project. So actually, all then are ready. The only one that's not fully operational or available yet is machine learning. And the only one that's in blue is the one that we actually applied for funding to attack. And I link that to management decisions. So we have a reaction time. That's a normal forecast that we have for a week to 10 days. We have what's more in the planning kind of scale, few weeks to seasonal, few months. And we have our call policy making or long time planning. So that's climate change, looking a few years ahead. So let's look at a few examples. So reacting, and I'm going to use the example about marine heat wave because that's one of the key things that we're looking to this project. So extreme events, specific marine heat waves. So every day we provide maps around New Zealand of what's going to happen the week ahead. So are we developing a marine heat wave in the specific region or are we not, right? So a marine heat waves here defined as the sea surface temperature. So, above the 9%, 4 or 5 days or longer. So classic definition. And that's aimed to everyone that can just look at the map and say, oh, is my region developing a marine heat wave? So it should be easy to read. But we have more specific users and need more details. So that's the example to the right. So, and that's the actual example that happened maybe 2 months ago of a fishing industry representative that came to us and say, I fish around the Auckland Island, and that's the 30 square 602. And they say, oh, I fish for squid at 400 meters. And what happens the last few months, I haven't been catching any squid over there. So what's happening? And he puzzled about that. I said, okay, great. We can actually go back there and look what the temperature was. So that's the map on top. So the time series on top is the surface and then the 400 meters. And what we saw is that actually temperatures were way above average at this time of the year. And now we're working with him to look at the whole time series back 30 years in the past to correlate his catch with temperature and try to link that into a forecast system. So to give him an alert system and say, okay, yeah, should we go there or what can we expect when you go out there? And that's one example, but they have quite a few more linked to salmon farms, mussel farms, you call it. Another good example is about storm surge and tropical cyclones. So this year we had the strongest tropical cyclone in registered history in New Zealand happen. That's called Tropical Cyclone Gabriel. And that's what we show right here. So I show what the winds and rainfall was doing, and then what the storm surge was. And then we just get specifically the time series to the left, actually specific points in time or specifically a location, sorry, and show what the surge was. So again, we provide that to this towns. So those are all towns, Auckland, Whangarei, Whakatane, they're towns in New Zealand. And those are not by accident. They're places actually we're providing an alert system based on that. So that's surge, but then what they want to know actually is total water level. So, and they provide us thresholds and we can say, oh, is that a risk that's going to be above your threshold or not? Cool. Then look into the next time scale. So in the planning, a few weeks to a few months. We decided that to try, instead of going couple models, that would be the traditional way to attack this kind of couple atmosphere ocean, to attack this kind of timescales, is to try using AI and machine learning. So what we did here is we decompose the signal of the anomaly, in this case for temperature anomaly, and then we apply this technique, this temporal convolution neural networks to the different components, and then we stitch them together. And that's what I'm showing you. So in the top is the total signal, and below that are the different decomposed signals. And everything in black is the true measure, and everything is in blue is the predicted one. And we see that for the all lower frequencies, it works very well, and actually doesn't work that great for the very high frequency variability. But when we put the signal together, actually those lower frequencies, they account for most of the temperature anomaly. So just look at the top one and see how the black line, the truth, actually approaches very well, or sorry, the blue line, the model approaches very well the truth. So it works, it's working nicely. We're still testing for different regions. It's not fully operational, but it's just details away of being fully operational. And then policy making, climate change. So we got all these model configurations that we had, and then we nested inside a few different global models looking at different scenarios. So we chose in particular 2 scenarios, one mid emissions and one high emission scenario. and we run for the mid-century and end of the century. We just run the mid-emission scenario for the mid-century because they're really close together. So it doesn't, they don't make much difference, but by the end of the century, they start diverging a lot. And then we can start looking just what the temperature is doing. So that's what the mean surface temperature is around New Zealand. And then we look at the different scenarios. By mid-century, what's going to do? And by the end of the century, and say, yeah, okay, nothing new here. Things are warming up quite a lot. Especially we go high emissions by the end of the century, huge differences, right? So not a huge surprise here, but what can we do with this kind of things? Because now we have this full 4D view of what's going to happen in the ocean in the future, and downscale it to the tails of the coastal ocean. That's where people want to know what's going to happen. So we can link that to uses action. Just go ahead, everything. Cool. So then we got to the industry and say, okay, one of the things that they were attacking in the Mona projects, connectivity of key economical and cultural interest species. And two of them are the green leaf mussels. So that's an endemic species of mussels of New Zealand, very popular, very important for the economy. And Paua or abalone, and again, very important for New Zealand economy. And so we got some of our partners doing some lab experiments and say, okay, what's the sensibility of the green leaf mussel for temperature? And what we see is that when it reaches about 24 degrees Celsius, they start suffering. What it means they can lead to mortality, but more important than that, even it leads to loss of productivity. And what we see today, so how many days per year we have at 24 degrees Celsius, and what's going to happen by the end of this century. And we see that a lot of the areas that we have the big actually mussel farms nowadays, they're going to have several days in the year they're going to be above the threshold. So I mean, they can expect. So what they can expect loss in productivity. So what we're giving them is this information so they can adapt to what's going to happen next. And the one below is the Paua or abalone. And the white wine shows the 21 degrees, and the 21 degrees is where abalone actually develops to a size that's commercially viable. And what you see what's happened today is that the whole South Island is actually below that. So that's why all the fisheries actually comes from there. And the map on the right says what's going to happen by the end of the century. So a lot of those areas where we have a lot of fishing now, they're not going to be viable by the end of the century. So then we're linking with all the stakeholders. We have 4 times a year, we have stakeholders meetings. We have people participating in our boards, helping to lead decisions and try to measure all this impact, and now to put some dollar figure on the side and say, okay, how much benefits in terms of how much money are we saving by those tools? And that has been calling a lot of attention in the media, and I'm just showing a few examples of articles that we have and interviews that we have of people really interested. So we just have been constantly in the media around New Zealand and Australia. So we had over 206 articles published in the last 3 years. Cool. So just to conclude, some takeaway messages. So Mongo Party works. It's a really cost-effective way to have an observing system of the coastal ocean. It's pretty cheap to run. So the whole system from observations, deploying sensors, getting back, assimilating, providing the information back to the users is, I say, 500K to $1 million New Zealand dollars per year. What's less than 500K euros per year. Just pretty cheap for observation and forecast. And how do we link that? So it's a full automated system. So it's completely linked to our forecast system. Doesn't need human interaction most of the time, as you that work with operations know. It's integrated into the ocean decade. So we are now doing the OSSEs as part of the SynOps initiative. So running between 2020 and 2022. And we're now linking to WMO. So we actually provide a test template for providing those observations through the GTS. So everybody can have access to that. We're just waiting for approval. And we are actually now analyzing what's the impact on the weather forecast. So we intend to present that on the meeting next year WMO is going to have. And I think I'm just going to stop here and just say that all the code that developed is freely available. We're happy to provide access to that. So all the data simulation, observations, data pathway, quality control, that's all open and available. Yeah, and we're strong supporters of the fair and care principles, because we work a lot with a lot of traditional partners. Cool. Thank you.
Thank you so much. Any question? Yeah, two.
Thank you. Morning, Joao.
Morning.
Wow, it's a wonderful tool that you've come up with. You call it a hammerhead shark, right?
Yeah, exactly. Mangopari, hammerhead shark. It's
Okay.
the spiritual guide animal of our main Iwi partner.
Yeah. Okay, it's amazing. Actually, I do think the fisheries industry really needs this type of help, especially from the region I come from, Southern Africa. But what I'm wondering is, how does the instrument really work? I probably missed this part in the beginning. Are you saying it pops up on frequency every day, or it pops up when it's proximal to a fishing vessel? And okay, maybe let me just ask all my questions so that I'll leave you with the mic. And also, I was just wondering also whether once the instrument pops up and gives the data away, is there no concern that given the troll traffic, for an example, because that's one of the concerns that's drilling on the trolling areas, there is a potential of a mistake of it being caught by the net or maybe stolen right away. So are you not having those challenges? Thank you.
Thank you. So it actually attaches to the fishing gear, and we have different mounts to attach to different fishing gear, and it changes strategy depending. So the firmware itself is programmed to change strategy depending on the pressure variation. So it senses that pressure is changing, goes to a higher frequency to actually profile it well. It senses that the pressure is not changing, so it's like a pot, like a crawfish pot sitting in the bottom, and then goes to a lower frequency, right? So pops when the fisherman retrieves the gear, it pops out of the water, then communicates through Bluetooth with a deck unit that's sitting just glued on top of the vessel, and that's completely independent. It's solar powered. And then this deck box is actually who communicates or sends the observations back to us.
Yeah, thank you. Great talk. I also have a question regarding the mangrove para sensors. What are the parameters that they measure? Can they be extended with the water quality parameters? And the second question is, of course, putting on the fisher boats is great for the cost, though. But have you considered extended also putting, for example, for the ferries or some regular also ships that also go offshore and have regular trucks?
Yeah, cool. Thank you very much. Yeah. So I actually forgot to say that it measures temperature and pressure. The idea, yes, just temperature and pressure at this point. The idea is that we want to have a proof of concept. So we said, what can we do? What's the most important variable that we can measure for our physical models, right? That's really simple. And we say, okay, temperature is going to be the most determinant one. Yes, and that, yes, I'll say for in general, if I have to choose, I will still stick with temperature. But then salinity, yes, is something that we think about. The problem with salinity is because sensor drift. And we want something that doesn't need, that's low maintenance. So basically we put that in the vessel, it stays there for 2 years without needing calibration. So because, we can't try and interact with all these fishermen all the time. They're going to get tired of us and they're not going to do it. So that's the whole goal behind it. So as simple, it stays 2 years. After 2 years, they send back to us. We change the batteries, recalibrate, and send them. Salinity is the next one that we're looking at the second phase, and that's kind of something that we're looking at. Salinity, again, problems, battery consumption and drifting of the sensor. So we worry about that. And there are some groups looking at the biogeochemical variables, more specific to fluorescency. So to have a fluorimeter, but again, the problem with optical sensors is that they're really hungry on power, and we have a lot of incrustation and kind of the problems and drifting, so it needs more frequent calibration. So there's a group in Woods Hole that's actually trying that, but right now it's like early days.
So, Joao, thank you very much. We started in Europe in 2003 to implement a fishery observing system, it's called FOS. And I send you 2 papers where we describe what we did and the assimilation.
Cool.
So one thing, however, that my remark is that since this is very powerful, we prove also with the data assimilation. is an enormous data set that we should really ask you to help us to coordinate this. We have two big efforts on fishery observing system in Europe. One is the Adriatic one, the one that we were involved with, and the other one is Brest, Ifremer. Okay, so we know this fragmentation, we have fragmentation numerical modeling, we have fragmented observing system. Help us, with Juliet, maybe you get together, because this is very powerful observing system, as you are saying. And there is already a lot of work done also, and it might help to evolve. So these are the two fishery observing systems that were set. The first paper is 2007, but we started in 2003 and then it was many people here were present, and the Brest one even continued after. So we need to get together on this observing system, because it's really very good for the coast.
Yes.
Please.
I agree.
Thank you.
Let me just comment on that quickly. So yes, Nadia, well, I'm well aware of the French system. We were inspired a lot, and we're trying to learn about the successes and what didn't actually work, and try to, say, so we can improve on where things didn't work. No, I didn't know about the Adriatic one. But that said, so what's happening right now? I think we are the one that has the biggest rolled out system. So we have over 300 sensors in more than 200 vessels in the water operationally. So I think that's great, because it actually covers the whole country. Japan has a pretty cool system, but smaller. I think they have about 20 vessels, something like that. Australia is starting right now. So what did we do? We actually founded a group that's called FVON, Fishing Vessel Observing Network. We're going to have our first meeting in Mallorca before Oslo. So we have people from France, we have people from Portugal that are really interested in trying something that. We have us, we have people from Japan, we have people from Australia, we have NOAA represented. So that's going to have our first meeting. And what we're trying to do right now is to draft what the best practice will be and share experience. And our idea of the system is to be so was developed as research. Even the way the Met Service in New Zealand works a little bit weird, because it's a company, but that was research, and everything's open, and we're happy to share. That's why all the code is open. Those sensors, we don't make a cent when we sell those sensors. Actually, the company developed that does make money out of it, but it is to be cheap enough that it's easy to roll out. So yes, for sure. Yeah.
Put you in contact with. There is a question from
great.
Alban online. Alban, please try to pop up.
Yes, thank you. Hi, Joan. It was just this question might be already asked. Can you
hear you?
I can hear you.
you don't hear me? Sorry.
Switch on your mic. No. Try now.
Is it now?
No. We can't
Now,
hear you.
is it okay? Do you hear me?
No.
No?
Is the
Oh,
audio
sorry.
on?
Or maybe write it down and someone can read.
Yeah, it was
Write it down in the chat. I'm sorry for that.
cost.
Sure.
Interaction with the fishermen about the services, because in our case they say, well, we are on the sea with the bad sea with the wet hands. So are your services coming on a laptop or on a mobile phone? We don't have ways to check the forecast when we are on the boat. So what's your experience with that?
So that's a great question, because the interaction or engagement with fishermen, I think, is frequently overrated. It takes a lot of work. And the whole idea is that they told us what they need. So we started by developing a little app, but you can't give too many things for them, because they're just going to work with the kind of tools they're used to. So in New Zealand, by law, they have to register the catch on an app. So what we're doing is that we're linking the forecast directly in the app they're already using, because they already have to register the catch anyway.
Okay.
Yeah. And so they get the forecast and they get also their own observations online. So they know, oh, I'm fishing here, and then they get the sensor data back right there. So they know what the temperature is. Because another thing that I learned is that the fishermen, they know a lot about what they're doing. And they understand a lot more than I imagined to begin with about ocean science.
Thanks.
Regarding the modeling effort shown, are surface currents publicly available, and what is the domain area? So yes, all the results are publicly available, not only surface, but the whole 4D. The domain is around New Zealand. Sorry, I don't remember the latitude and longitude exactly, but our data simulation system is a 5 kilometers domain around New Zealand. Just go below the Auckland Island to above New Zealand, so encompassing the whole EEZ. But again, as the whole data simulation scripts for post-processing, observation, everything's public. So yeah, happy to share.
Thank you, Joel. Thank you, Lars. So I'm now calling George Diatis online. Unfortunately, George couldn't come, but should show up. Yes, we see your screen, George. We don't see you.
Just a moment. Okay,
You're
just a
talking, we
moment.
are not hearing.
You hear me? Good morning.
I guess.
Hello, good morning. Hello? Hello, good morning.
George, are you trying to speak?
We can
Yes, I
hear
speak.
we can hear
You
you,
hear me?
but not in the room. I think
George.
they don't hear us.
So is a problem with our audio.
Hello?
Okay.
My God. Giovanni? Hello? Oh my God.
George, wait a minute. They are fixing their audio.
Okay, okay, thank you.
Welcome.
George, try to speak now.
Yes, you hear me?
Now, yes, perfect.
Okay.
Please go.
So can I start?
Yes, try to keep it 10-15 minutes.
Okay, okay. So good morning to everybody from Cyprus. Okay, I didn't know about this problem with the sound anyway. So it's obviously from my presentation, the title and the people you see from the first slide, that the example I'm going to present is a teamwork with collaborators from Cyprus, Greece, Italy, CMCC and University of Bologna, and from Spain. So the outlines, just a few words about the downscaling of operational oceanography in the Eastern Mediterranean, in particular the Psychophos system, the challenges, the motivation in respect to the example I'm going to present about the oil leakages, oil slips from shipping and traffic and other, the related European Union directives and the Barcelona Convention, example of the recent downstreaming application in the Eastern Mediterranean Levantine Basin. So just to remind to all of you and follow later on from his presentation in EGU 2012 about the revolution in our science in oceanography in respect that nowadays we have the satellite altimetry, we have the in situ information, thousands of the arc floats, and we have the operational oceanography initially in the frame of MyOcean, the 3 projects. And of course, nowadays we have the Copernicus on a global and the 6 regional forecast system of Copernicus. So in the Eastern Mediterranean, we have the psychoforecast system that it is first started to produce its own forecast, downscale forecast from the MFS, the Mediterranean Forecast System, in the frame of the legendary project of the MFSPP coordinated by Professor Nadia Pinarti. So we running, of course, the system is periodically is improved. And at the moment, we're running two models, one for the Eastern Mediterranean with the resolution 2 kilometers and for the Levantine 600 meters resolution. The model periodically, as you can see from the slide here, it is receive validation calibration. So we know that the results are good. The same time, we run in operation running the wave model. We're using the latest version of the VAM model, the ACMW model. And also in the Mediterranean and in the Black Sea, we're using the Skyros wind in order to produce our wave forecast. And again, also it validate periodically using in situ information from available buoys around the Eastern Mediterranean as well as in the Black Sea. So the motivation, the challenges we have in respect to the coast predict activities. In the Eastern Mediterranean, we have the last 10 years an increase of oil and gas exploration in the EZ of Cyprus, in the EZ of Israel, and the EZ of Egypt, as you can see from the map to the right. The big companies like the Italian Eni, the Total, the Shell and GoGas and many other companies, they are drilling in the area. At the same time, we have the approved plans, the map to the left of the deployment of the from the east to west of the gas pipeline in order to transfer the gas from Cyprus, Israel, and Egypt to Greece and then to Italy. And of course, this is ongoing activities. Then, of course, the last year we have the enlargement of the Suez Canal, where the traffic of the tanker passing through the Suez Canal, it was estimated to increase by 25% compared to previous tanker traffic. And also we have verified that indeed there are thousands of oil slicks from identified by satellite images, as you can see also from this image here to the bottom. So then we have the European directives and regarding the maritime safety, the European directives 2013-20 concerning the obligation of the member states to act in cases of offshore oil and gas platform leakages is similar to the MODNET, say, Med Sea and Black Sea checkpoints. It was one of the challenges, the oil leakages we examined those days. The project was coordinated by Nadia Pinarti. And then we have the European Union Directives 2005 and 35 concerning the obligation of the member states to act in order to identify the source of the oil slicks from the ships. Of course, in addition to these two main, say, directives, there are several others related to these base activities and directives of the European Union. Then, of course, we have the Barcelona Convention that is signed by all the repatriant countries in the Mediterranean. And in respect, they have several protocols. One of the protocols is the offshore protocols that is urging the interested parties, the government, as well as the industry, to proceed for impact damage assessments in order to assess the consequences of oil spill leakages from planning as well as existing offshore platforms. And of course, in this impact damage assessment should be included and based on oil spill simulation. Without this is not valid. So why? Because it's obviously that from the oil spill application, we are getting information where the spill will move, how soon will get there, the first impact on the coast, and most importantly, which resources are going to be threatened. In order to provide this information and the information to be validated, we need first of all quality control data on the sea currents, on the waves, and of course on the winds. This information nowadays provided by the downscaled forecasting system in the area. Of course, thanks to the Copernicus system that will provide this. So as one of the first example is the challenge on all these leakages from the Leviathan offshore platform in the east of Israel. Leviathan well is the second largest oil and gas exploration in the Eastern Mediterranean. We have approached by a local authority from Israel. There are concerns about the offshore platform that is located 10 kilometers from from the shore. This offshore platform receives oil gas from the Leviathan field that is located 120 kilometers from the Israel shore. And it was an important concern that if anything will be happen, the damages from the condensate oil, because we have the pipe, they transfer gas, but together with the gas, they transfer also the condensate oil that is the threat to the coastal environment. We have done this study together with partners from Greece, Cyprus, and of course with CMCC and the University of Bologna. We presented the main results in the INGU 2020, and a relevant publication I hope will come soon. Then, of course, some basic maps from this application that, of course, if something would be happen, then, of course, a larger part of the coast of Israel will be affected. Recently, say 2 years ago, in August, of August 2021, we had the second biggest oil spill incident in the Levantine Basin, the oil leakages from the Banya power station in Syria. This spill is the second, is the same order of magnitude and the type of the source as the one of cases in back to 2006, the known Lebanon oil spill crisis. Of course, in order to do this simulation, it was a request from REMBEC to the Mongoose members to activate the emergency response office. So together with CMCC, Giovanni Copini, Orion, me, and partners from Spain, we have provided this daily forecast using satellite data provided initially from EMSA CleanSeaNet as well as directly from ESA. So, and due to the fact that in that period we have a strong currents between an anticyclonic and cyclonic eddy between Cyprus and Syria, it is these two features are features of the dynamic of the dynamic of the area, and the calm conditions of the wind. It was somehow it was the spirit was spread offshore, affecting a large part of the northeast Levantine Basin, and of course it was a minimal say oil beached on the coast of Cyprus and Turkey. Most of the oil it was landed in the coast of Syria. So during this application, we provided to REMBEC and also to the repatriant countries like Cyprus, Israel, and other countries in the area who they are concerned about these daily bulletins with the basic information. In addition, in the same year, in February 2021, it was again an oil spill in the east of Israel, where the spill it was spread and affected 160 kilometers of the coast in Israel. It was a big issue in the media. So again, it was a request from the Ministry of Environment of Israel to Rembek, and then Rembek to the Mongoose member, CMCC and Orion. We have tried to provide these OSP predictions in order to identify who was the responsible. It was different version. Either it was a Greek tanker passing from that area, then it was an Iranian tanker, and then also it was a pipe that it was abandoned many years ago, and maybe it was some accident there. So this was again an application. Then again, recently, last year, this is a very, very coastal application, again, using the downscaling forecasting system in Cyprus. In this part of Cyprus, it's a famous tourist area, Gianapa. I mean, the Europeans say, people, most of the Europeans, they know the place. So they have constructed and deployed an underwater park with 93 submersible sculptures in the depth up to the maximum depth is 10 meters. And the name is Musan. If someone is interested, you can see the web page from where you can see this underwater park. It's considered very nice. And a famous Spanish architecture, he has designed all these sculptures in the area. But the request, it was to estimate the extreme wave events from December 21 to April 22, and most important, to estimate the dynamic pressure from the waves at the sea surface, the 2 meters and 4 meters, who they case damages to these underwater structures. So for this application, we have used LiDAR data with 10 meters resolution. We blended this data with a high resolution from Edmonton because we had to enlarge the area. And we have put the boundary condition, the wave boundary condition from the cyclophos forecast system, and above the forcing the wind forecast in the area. So we have estimated that this period we had 7 extreme events and 7 high extreme dynamic pressure affected these underwater structures, and they make the damages. The authorities, they were satisfied on the results, and after we have delivered the report, they told us that it did the end of December. This is in red here. It was monitored that the damages were cased. So the forecast and the study was confirmed by the people who was interested for this. So the last one, it is the mass stranding of 15 Mediterranean whales found dead from 9 to 12 February 2023 along the northwest coast of Cyprus. So it's here. Initially, the authorities, they thought that this is a consequence of the catastrophic earthquake in southern Turkey case on the 6th of February 2023. I am sure that you know about this issue. And of course, another possibility source is the stranding and the death of the whales. It may come in from the intense underwater pollution, noise pollution, caused by the use of specific sonar of Navy subsea exploration. From this map here to the bottom, you can see these small areas where it was reported by NAVTEX that it was, say, defined as area for Navy exercise, different countries. It was Navy from USA, from Russia, from Israel, and I don't know who else. So it was coincide the same period. So the request, it was to define with a trajectory prediction from where these whales they may arrive in the coast of Cyprus. So for this case, we have used this downscaled cyclophos forecast, the Skyron wind, and we have produced these trajectories that is shown that they directed to the say west direction. They came from the northwest direction because the application was a backtracking. And then we found an information that a seismographic research vessel, it was carried out its activities in the same area where we have predicted that the whales they came from. So most probably, I don't know what kind of activities they had, but if the whales they just landed on the coast and they dead, so it seems that they use kind of explosion for their seismic activities. So as a last words, they provided downstream examples that get in the challenges of oil slick leakages from offshore platforms. What?
Can you come to the conclusion, please?
Yes, I'm finishing now. Yes, saying that they provided downscaling example targeting the challenges of oil spill leakages from offshore platforms, for the maritime traffic, the coastal recreation facilities, the marine life give strong evidence that the operational forecasting at coastal and sub-regional scales is indeed useful for the key end users, the national and regional response agencies in the Mediterranean Sea. I take this opportunity to propose, if it is considered, to include the Levantine Basin as one of the study of the coastal prediction due to this activity, especially to the oil and gas activity in the Levantine Basin. Thank you for your attention.
Thank you so much, George. It's really a clear example of providing services to society and to stakeholders. Any question for George? Online.
George, what is your evaluation of the improvement of the system in the last 10 years, let's say 2015, 15 years and 23?
I mean, you mean the hydrodynamical and the wave model, yes?
Yeah.
As I have, yes, as I have presented just a few slides, that we do periodically validation with in situ information, with ARCO floats, with satellite data, and with the PEREM model, I mean the MFS model that is running under the Copernicus, and the statistics and the metrics are we are very satisfied. This is one. Secondly, the wave model, again, as I said, we are using any available wave data in situ monitoring. And also important, and I think is something that will come in the next, say, few weeks. It is paper on the oil spill on the Syria, where we have compared the predictions of the MESLIC and the open drift model with the satellite data, and the statistics, they are really good. Unfortunately, I don't have these statistics with me now, I mean, in the presentation. So what I want to say that I am very confident on the Psychophos forecast, because I said, again, we compare, say, periodically and constantly with in situ, satellite, and the PEREM model. And the result we are getting from the applications, the end user applications that confirm at the end of the day what we are presenting. I think that is good. It's good.
Okay, thank you. There is a question from Christina Forbes from US Coast Guard. She's asking, how did you backtrack where the whales came from?
We are using the MESLIC, say, trajectory prediction model. So we have using the sea currents in this application. We have done it. We have used the sea currents of the downscaling Psychophos forecast and the wind. In that application, we didn't use the wave data for the backtracking, but it's possible to use it. We have the facility. The possibility.
George, thank you. Now we move to Marco Marcelli from University of Latouche and CMCC, and they will present the Renovate project.
Good morning to everyone. That time here I am in representance of all the researcher groups that include. So that include University of Tuscia, CMCC, University of Milan, 9 universities more or less, more than CMCC and OGS, Italian Institute of Oceanography, and CNR. So, as we know, the coastal systems are affected by a big conflict between the users and resources. So in our case, we focused in the Civitavecchia area where we have everything. And in the last years, we have also problems regarding the climate change impacts, in particular, as we see the heat wave effects on Posidonia oceanica and dramatic effect of the Medicanes and huge storms in Mediterranean. Always we can see now on Posidonia that we have never seen before in our coasts. So we have to face these problems, but other critical impacts arrive from the human activity. In particular, in this case, there is the expansion of a big port in the Mediterranean Sea, that is Civitavecchia Harbor, and this expansion has direct impact on benthic bioceanosis and on marine protected areas, indirect impacts, in particular on Posidonia oceanica, coralligenous reefs, and protected species as Pinna nobilis and Corallium rubrum. So we build a big project, the Renovate project, that is a long-term project that we decided to build to develop an approach, a new approach, an ecosystem approach applied to compensation and mitigation action in the coastal marine environment based on the restoration of ecosystems. In this case, we wanted to recover the ecosystem services that the ecosystem lost during the port expansion and due to other human activities. So the objectives of our project is the compensation action on the environments and the restoration of the ecosystem services, the creation of an early warning system to manage it's difficult for natural events, but to manage ecosystems but also to prevent impacts from dredging activities and other human activities, to build a prototype of digital twin of the ocean to support marine ecosystem restoration, and the development and implementation of an innovative observing system based on the integration between the numerical models, in situ measures, including new technologies and so on. The funding are 5.4 million euros now, Italian project, and the partners, as I said before, is CMCC, University, OGS, CNR, more than fishery, divers, citizen science, with more than 40 researchers involved in the activity. But the innovative of the project is a long-term project, so a 10-year project, so we can have the time to understand, to develop the new approach. And in this slide, we can see the complexity of the project that see in the middle of the core of the project are the numerical models that address the activity of restoration and address the activity of compensation, mitigation, and define the quantity and the location of the restoration activity and of the mitigation activity that are also other activities like artificial reefs for recovery of several species and so on. That is also a lot of steps that we have, including the to manage an action of integration of our activities with the environmental ministry activities that are in arriving on the ecosystem restoration field. So the first action was to build a big observing system that in this case is based on autonomous platforms like gliders and autonomous surface vessel, buoys, a DCP, weather station, traditional methods, coastal radar, traditional surveys, characterization of the biogenesis, in situ experiment, in lab experiment, and all those actions are integrated in numerical models and in statistical models. Upper we can see the invest model that has been developed by Stanford that we use in this case to calculate the carbon storage, and we calibrate the model with in situ activities with benthic chambers. In bottom we see the operative model that has been built by OPA division of CMCC, and that has a higher resolution on cost, and we can use to integrate the forecast system to prevent accident and so on, and a lot of other simulation to support the ecosystem restoration. On left we can see the velocity of the orbital velocity of the waves, so that we can decide, for example, if there are several places that are not good for restoration activity in front of other that are better situation. And we arrived at the concept that is have to support all the ecosystem restoration, that is the digital twin of the oceans applied to ecosystem restoration. So ecosystem that the ecosystem give us in terms of ecosystem services, we consider the stress on the ecosystem services, and so we can decide the what-if scenarios, and we choose the restoration action, and in terms of both terms of quantity and quality of the restorations. So the feedback, the numerical models can give us feedback about what we are doing. Through the observation, we see if the numerical models and ecosystem restoration action has a good results, because we have 10 years to understand it. And inside, for example, on Posidonia oceanica, we want to analyze the wave attenuation. So we realize the stressor is the infrastructure realization. The what-if scenarios can regard the siting and the optimal design of the restoration action. So maybe is a patch technique, another technique. We can choose several techniques to have the better results. And XXX, because I don't know the name of the numerical model, so we will develop by university, in particular University of Bologna, that is involved too in the project. And through the ecosystem service measurements insight that we continue along all the project, we and the other observation, we can have a new insight. So we can decide if we have to change some things. Now, we started a few months ago, so we are starting with the activity. I hope next time we will have the first results we encounter, and the expected outcomes of the project is to support the governance for a sustainable development of the harbor, because it's a big harbor, longer term experiments, as we have seen, the development of an integrated, not only integrated, but also innovative observing system, because, for example, we will include in this kind in our project, to face the problem of heat waves, also thermistor chain along the coast to have data continuously when, so we can see immediately if the models and the satellite data, how we can correspond those to the low cost instrument deployed along the coast. A high level of innovation, deep knowledge of ecosystem services, best practice of restoration that we are starting to. It's very difficult to put together so different field of science, starting from physical oceanography, arriving to genetic of the oceans. So as and is a big goal. And last but not least, there is also the objective to create a center for marine communication and education in the harbor. So thanks for your attention.
Thank you, Marco. Any question? I have one. Which are the innovative sensors you are talking about? I mean, which are the innovation, especially when you look to which are the new experiments that you are doing for nature-based solution and restoration activity?
For example, in this case, we have designed one of the biggest experiments in lab and in field together to measure in field ecosystem services. For example, measuring exactly the carbon storage, the oxygen production, and other services from Posidonia oceanica, from Coralligenus, from Schistosera, for several different habitats. In labs, we are in parallel wave. We are experiments the tolerance of the single organism and of portion of habitat to stressors, to human stressors. For example, sediments. So we know that in the early warning system, through the numerical model, say where the plume of the dredging activities arrive, and we know exactly the tolerance limit of the species to the dredging activity, so that we can block we can stop the activity of dredging if our prevision will give up. Is clearly because in Italy, in other countries not, but in Italy, the port authority is of the state, is an agency of the state, so they have no interest, commercial interest. So if we say stop, they stop. We have seen in past, because they are from transport ministry, so it's more easily that with a private harbor.
If I can comment, and this is a message also for Nadia, I mean, similarly to what you were proposing about low-cost innovative sensors and citizen science, I think we could imagine to network the different restoration experiments, because we saw this morning Joanna and then and now Marco. So maybe we can really, because we need to define best practice of in restoration and how to use the models, for instance, and the observing system for the restoration. So Yeah, sure, sure.
Yeah.
Because we need to calibrate the models. I mean, to even to develop a part of them. So didn't ask directly to the engineers. We did.
So yeah. Yes.
Okay. We are very late, but I think let's keep it in mind. I mean, let's network on this. Okay, let's go to the next presentation. Thank you, Marco.
Thank you very much.
Kululeku. Yeah, please. We need to try to stick to the 15 minutes, including questions. So I will send up a few minutes before.
Thank you for this opportunity. My name is Gululego Memela. I'm from Cape Town, South Africa. I'm here to present to you the teamwork which myself and my team are working on. I thank you for this opportunity to present and share Southern Hemisphere and reduced resources perspectives. So I'm going to talk about South Africa's recent operational and ocean forecasting journey, the journey of many challenges, and these challenges we share with many of our neighboring countries. These are challenges that range from lack of in-situ data, lack of human capacity, lack of infrastructure, lack of bandwidth, but I should dare stress the lack of human capacity is the most serious in my view. So there's my team, and that's my name. But I also like to show you the oceans of South Africa. So let's not forget the complex nature of our oceans. We are bounded by the cold eastern boundary system, the warm western boundary system, and we have the interaction between the two. So because of this reason, we are hard pressed to find products, global products that can accurately capture both regimes. And with warm biases being the norm in the Benguela region, the frontal regions like the Agalas, its retroflexion, and the return current being problem areas when we're using global models, we have seen that there is a serious need to have optimized Southern African models that can model the Southern African coast regionally and to a coastal level. So this is something that our government has eventually recognized as well. So in the ratification of Operations Pakisa, which aims to sustainably exploit and grow South Africa's GDP based on the blue economy, the South African government has put on the Department of Forestry, Fisheries and Environment the responsibility for marine protected services and good governance of this program. So that's the work stream number 4 of the 6 work streams of the Operations Pakisa. So to this end, the Department of Forestry, Fisheries and Environment, together with CSIR, have developed what we call OSIMS, but OSIMS is the National Ocean and Coastal Information Management System. It provides customized decision-making support tools to stakeholders, and they do this in an iterative process. So they don't just develop, or we don't develop the tool for the stakeholder, but we work with the stakeholder up until the tool is developed so that there is no wasting of time. As an example, I'll show you one tool that is already existing in OSIMS. This is a harmful algal bloom tool. So it is based on satellite information. It's able to provide a matrix of probability of harmful algal bloom occurrence in key locations along the coastline. So this support tool was developed in collaboration with aquaculture, which is one of the stakeholders. The tool came as a response to the 2016 devastating harmful algal bloom event. So it became apparent that the need for tools like this is very strong. So the tool does not have any ocean modeling in itself, which brings me to SOMISANA. SOMISANA stands for Sustainable Ocean Modeling Initiative, a South African approach. You can call it, we will stand together. That is one of our South African languages, Sipedi. It means we will stand together. So that's the meaning of the word SOMISANA. But we like the word, it means many positive things in South Africa. For an example, another language in South Africa is Xhosa. It means we will work together. So we like the name SOMISANA. It captures a lot of what we do in our team because the aim is to work with the stakeholders. So the idea of working together is seriously there. But on top of that, the aim is to produce a mass base of skill sets. So we were trying to create experts that will be able to do ocean modeling. And we are also trying to support the work of OSIMs and give them operational information that they can then share with the stakeholders. So I also like to show to you that we have gone to the focus model, or we've developed a focus model. So in developing a focused model, we had to choose a limited area domain. We couldn't just focus the whole of Southern Africa or South Africa because we wouldn't be able to immediately track the effectiveness. So we decided to choose the small area. The small area, if you can see the Port Elizabeth down there on those pointy arrows. Around Port Elizabeth, it's now called Gqeberha, by the way, the city has been renamed. So, but around Port Elizabeth, we have a bay called Algoa Bay. We selected the Algoa Bay as our region of interest for initiating our experiment, our prediction or our initial model. So we've developed a model on that region. The many reasons why we chose Algoa Bay is because it is advantageous compared to many other places around South Africa. The advantage is that there's many bed colonies. The other advantage is that it's a CN Sentinel site, which means it's well monitored. It's also having lots of oil spills. Am I out? All right, sorry, I didn't mean it has lots of oil spills, but it is also a site for oil bunkering. So that means we are able to have ship-to-ship. We are able to have ship-to-ship oil transfer, and as a result of that, it is possible to check the use of the model in a way that will interest the stakeholder. So there's many other reasons why we choose the Algoa Bay that I can go deep into, but I'll move on. We therefore went on into forecasting mode, and we created a curvilinear grid. The curvilinear grid we created is based on depth 3D tools. So it increases in resolution from the boundaries of around 3 kilometers to around 500 meters in the center of the bay. And this is allowing a seamless transition from the coarse resolution Austrian boundary conditions. And the model is based on Croco. So we tested the boundary forcing by running model in hindcast mode, and we did evaluations against temperature, against currents, and we were able to show that the results were pretty good. So the model is capturing the reality in a very satisfactory manner. We therefore went on and tested the atmospheric forcing. We wanted to see if there's any real difference if we use higher resolution winds and lower resolution winds. To our astonishment, the difference is not very significant. Actually, we can say there's no difference except for small scale variability. If the higher resolution model is used, if the higher resolution winds are used, we are able to see differences on small scale variability, but in the general grid level variability, there's no change. So as I'm about to finish, I'd like to also indicate that we tested the forcing of the we also launched into focus mode by allowing the boundary forcing and using the Mercator lateral using lateral boundaries. So we use the freely available GFS winds, which are a third of a degree, very, very coarse resolution. We know that, and but because we know the limitations of the winds we used, we are able to take into account the results that would follow. And on top of that, we have been offered by the by South African Weather Service higher resolution winds going forward. So this is an issue we will be looking at. In addition, we have added a rudimentary oil spill tracking function that releases oil spill at each of the bunkering sites. The bunkering sites you can see there. So we are releasing the oil spill every day to track the movement of the oil spill. So we're able to create a simulation that would help the stakeholder in the eventuality that they need such assistance. The tools are Dockerized, which means we're able to move this model and put it in a location of our choosing in the future if we decide to do the modeling in a different location, which we do actually intend to do because our list of things to do keep growing. We don't just want to model this Algoa Bay region, but we want to model the entire coast of South Africa or Southern Africa. So what I want to leave you with is this as I finish. We've produced a very simple system. It is easy to deploy. It's easy to redeploy to another location should there be a need. It's very scalable. We believe that this is the type of system or solution that can really help an under-resourced nation like ours or many of our neighboring countries. So, and we believe that its contributions can really help various ocean decade programs. I thank you.
So thank you for your presentation. I would like to know if you are planning to predict harmful algal bloom. So you said that it's a very dangerous event for fish farming.
Aquaculture, yes.
Yeah.
Oh, sorry, I didn't get the question. Say it one more time.
Yeah. Will you include in your forecast the algal bloom?
Our model is not really a biogeochemical model. We do have intentions of going that far at some point, but at this point, it is a purely physical model. But we have intentions of helping OSIMs because the harmful algal bloom tool that you are looking at is it's a tool of OSIMs. It does not really belong to us as Somisana, but because we provide modeling solutions to OSIMs, they will be requiring all sorts of solutions, potentially to even add a level of modeling to the harmful algal bloom tracking. Thank you.
So, but maybe you can also include satellite images in order to assess.
Yes, definitely. Because, and by the way, that's how it works currently, the harmful algal bloom tool. It's using satellite data purely.
Hey, thank you for a talk. I have to say that I have been following up what's happening in South Africa for a little bit because I have colleagues that work there, and it's really interesting to see where you guys are going. Maybe one piece of information that I don't know if you're aware, Gary Brassington at Bone in Australia is actually trying to initiate a group uniting all the operational centers in the Southern Hemisphere. So there was someone from South Africa included, but maybe something that you want to pay attention at because we're trying to share experience, learn with each other, kind of unify systems in the future.
That's amazing, actually. I'm with my colleague, Juliet right here. So definitely we'll have a talk after this.
Cool.
Oh, you're referring to Jenny?
Cool, thank you.
Maybe better.
And then a question, so you're going to pretty high resolutions and using Croco. And one of the big difference of Croco advantage is because it's non-hydrostatic. Are you actually going to non-hydrostatic modeling?
Non-hydrostatic.
Yeah.
Well, I apologize. I can't answer that question specifically because I just joined the team. I don't fully understand some of the deeper applications we may have performed in the background like that. But I'll be working further on this. So surely if we meet another few months from now, I'll answer a question better.
So thank you so much.
Thank you.
I'm calling Edgar Cabrera from IOC Caraíbe to present the project Integrated Coastal Hazard Early Warning System for the Tropical Americans and Caribbean. So we do this one and then we stop for the coffee break, I think, because coffee break was 11. So I hope, sorry, but we are late. So we will start with Begonia after coffee break.
Okay, thank you. And gracias, Giovanni, to Professora Pinardi for this invitation. My name is Edgar Cabrera, and I am from Colombia, physical oceanographer with a long-standing career in my country as an oceanographer and hydrographer. And then I spent some time, more than 10 years in WMO as head of the Ocean Affairs Division and then responsible of this marine program and the liaison between the IOC and the WMO. So yesterday there were several mentions, and I will recognize that and that there is an effort that we need to continue. I will make this presentation on the Ocean Decade project called Integrated Coastal Early Warning System, Coastal Hazard Early Warning System for the tropical Americas and the Caribbean. And as mentioned by Giovanni, this is an effort led by the Oceanographic Commission for the Subcommission for the Caribbean, IOCaribe, and the planning group that was established for the decade. So the contribution, main contribution for this program is come from Krista von Hildebrand Andrade, that is the lead of the Safe Ocean Group. So the coastal threats are real and getting worse. I don't need to convince you that this is a slide that we get to discussion, especially with the authorities, the stakeholders. You will see the tropical cyclone tracks or the hurricane tracks in the Caribbean that are becoming more intense and also frequently. And in the left, we have this tsunami events that were registered in the Caribbean, and the sea level rise with the different scenarios coming from this report from the IPCC on oceans and cryosphere, and the algal bloom, sargassum, sorry, the ocean coverage that is here presented we have a strong group in the Caribbean and led by the University of Florida. And the activities, that we have the fishermen, the tourism that is very important for us in the maritime transportation. How was the reaction of the group of the region? They say having this decade goal, okay. So we were proactive, and in the Caribbean there was established a coordination group or planning group, and you will see the 6 of the 7, let's say, objectives of the vision of the ocean. The clean ocean, healthy, productive, safe, accessible, and predicted ocean. And one is missing, is an inspiring ocean. And but we replace by the capacity development group. So the start is here on the safe ocean, because this group, this is the one that submitted this initiative. I was leading together with Albert Martis from Curaçao, the accessible and transparent ocean, and working also with the predicted ocean team. So there was a series of webinars that we conducted, especially with the support that received from the Norwegian funds. And we conduct seven workshops on these several areas. And I was leading one of this consultant team with 2 senior consultants and 2 junior consultants. So there was a very interesting group because, as Professor Bernardi said, perhaps we come from the old school, but have all this innovative and youth and energy. So it's very interesting and a good mixture to work. And we submit for the call to these projects coming from the 3 main, brands of the decade: knowledge and solution, essential infrastructure, and foundational. The one with our project on coastal hazard early warning system and service for the TAC is tropical Americas and the Caribbean, because we we look not only the wider Caribbean, but also the East Pacific tropical, so we have this name it as tropical and Atlantic, tropical Americas and the Caribbean region. So we have this project. We will have also the ocean observing and forecasting system for the region. This is really the IO-Caribe GOOSE, the global ocean observing system. And we have this contribution to the IO-Caribe, or the contribution from IO-Caribe to the Seabed 2030 project on the Mesoamerica coastal, Mesoamerica Center for Hydrography. And on all these other topics on best practice, social literacy, and capacity development. There were other projects that we considered, but we will not submit, especially the one that you have talked a lot about, the digital twin, because our perception after this discussion with experts is that we were not ready to submit this. So it's not that we are not considered, it's that we need to build better basics in the region. So the Safe Ocean Working Group, this is the schematic on the members for the country and some publications that were on this co-design Safe Ocean on the Western Tropical Atlantic. As mentioned before, was the Western Tropical Atlantic, and we moved to the tropical Americas and the Caribbean. There was a survey in 2020, and you'll see the results, and the results on this question that we raise or address to the public in the region is that what are the scientific understanding of threat, partnerships, education, observations, and the response with the most important for them is really to have the observations, data, and alerts as a basic. That recalled me yesterday there was a question on how we address this survey. So I revert to our colleagues in IO-Caribe, and they offer to use the system for your survey, and also for the one on the ocean forecasting that was mentioned by Mercator. So they are willing to use the system, and I am sure that with Professor Pinardi, there will be no problem also to use the WMO network to address these surveys. This is a schematic. Our colleagues from Australia, they are really proud, and Krista used this because and tell that they are the first one that they're breaking down silos. So we use this, but then the UNDR take as ownership, and it's no problem. But it really is how we work together, how we work together. There are several comments yesterday. We need to coordinate, to work, not duplicate. And this is what the spirit of these groups. So on the prioritization of hazards, also coming from the survey, the top 7 were the sea level rise, sargassum, tsunami, COVID, wastewater, hurricanes, and oil spills. So these were really the hazards that were considered for the consideration of the project. And this comes with the project that we submit. So the impact-based to evidence and impact-based integrated coastal hazard early warning system and services, addressing 4 key elements: monitoring, warning, risk knowledge, understanding, warning, dissemination, and communication, etc. To enhance resilience to this coastal hazard, and to address the threats, direct and cascading impacts, cultural, political, economic, social diversity. So all these social science that you mentioned, or may not do, several you mentioned yesterday. And capacity development, human, environmental, sustainability requirements, and inclusion of the most vulnerable, especially on the Caribbean, that there is the physical aspects are, let's say, complicated, but we can address it. Looking at your presentation on this development and oceanography, so it's okay. But the geopolitical aspects in the Caribbean is very, with a lot of complexity, and the difference between the countries that are in the continent, the countries that are in Central America, and the Caribbean, especially on the island and small island developing states. So this is a summary what we have. So the Safe Ocean, integrated coastal hazard. The IO-Caribe is the lead. So like I mentioned, this is a subcommission of the UNESCO, but it's taking the lead because it was the one that promoted, but perhaps it's not the proper organization that will lead this project. perhaps it's WMO or the UNDRR on the Caribbean, that I need to mention that in Panama, so in Panama now they have this knowledge city where all the main organizations are based. So the UNDRR, OCHA, the WMO is not there, but it's in Costa Rica, but perhaps it will move. IOCaribe is in Colombia, but it's very close. So Panama will be perhaps one of the linkers. Not as Panama, but at least as a site where this organization will work. So the program was endorsed and the cost predict. So we are very proud to be on the cost predict. And this is the reason because we are here. The 4 main elements I have already read, and 2 overarching elements. So it's the governance and capacity development. So really the governance is how we need to adapt on this project. And how to link with our as affiliated program to cost predict. These are the initial actions. So the one I mentioned already, the established governance and management framework that we are under discussion. To alignment of activities with existing DECAD programs and other relevant action, because we are linked to cost predict, but we are linked also to the other GOOS, the Global Observation System program, on the observations, on best practices, and also the tsunami program, that we need to work together. We need to know what observations and the marine science can make available or we have available by 2030, and this is more what you have already discussed and all these initiatives on the global ocean observing system, but also the academia and all the observations that they are undertaking. And define an initial activity, for example, a blue line that was proposed by the tsunami team in the Caribbean on what and who are at the risk from coastal inundation. But here, if you read this, is really, we want to be part of this global coastal framework. So to identify a site and to work in this new situation that you provide us as an opportunity. The partners, I list the partners that we have considered, and you see the extensive list of partners that we have discussed in the formulation of this project, or that are present in the region, and we need to take in account. This list continue for the different universities, regional organizations, or the med services that are responsible. There was a question yesterday on how to engage the med service in the Caribbean. The med service are deeply engaged, and especially because the sonographic services are not completely established as a service. So sometimes there are the med service that perform this responsibility. Krista sent this Ocean DECAD tsunami program as an example, because they have this new observation analysis technologies, the high uncertainty, the low uncertainty, dynamic-based capacity, the resilience on the communities, and then the comprehensive institutional community preparedness that we call tsunami-ready system. Not that the countries need to comply to a series of requirements and work together with the communities and be tsunami ready. These are other initiatives. We took this from the news last year. There was an announcement from the United Nations that we need to have this the so-called early warning system for all. That by 2027, all the countries need to have an early warning system established. So in the case of the Caribbean, it is a challenge because half of the countries or the island have not this system established. So how we come with that? And so there is the best practices, of course, from the United States, from France, from others present in the Caribbean. But in my country, especially in Colombia, they are ready to share this best practice and help as a priority for the Caribbean. This is led by the WMO and by the UN Office for Disaster Risk Reduction that is based also in Geneva and the same building of the WMO. So we have this week the formal session of the IOCaribe 17. And this presentation was delivered on Monday. And as there was a marine scientific conference, and there were several topics, and Professor Pinardi also delivered a presentation on cost predict. But these were really the recommendations that we submit to this group on the goose. So I perhaps highlight the other